Welcome back to The Explainer. Today, we're diving into something truly brilliant, literally, the science of sight. We're talking about optics, the field that explains everything from your reflection in a mirror to how the internet gets beamed across the planet. And it all kicks off with a simple question I bet you've wondered about before. You know exactly what I'm talking about. You take a perfectly straight straw, pop it in a glass of water, and suddenly it looks like it's snapped right at the surface. It's so weird, right? It feels like it breaks the laws of physics. But what you're seeing is actually a perfect demonstration of the physics we're going to explore today. Here's the secret. It's not about the straw. It has nothing to do with the straw. It is all about light. It's about how light travels, how it bounces, and, you guessed it, how it bends. As soon as we understand the basic rules that light follows on its journey to our eyes, the world, and that bent straw start to make a whole lot more sense. So, to get this all started, we need to meet the main character in our story today, the light ray. It's the absolute fundamental building block for understanding, well, everything you see. Okay, first things first, where does light even come from? Well, it all starts with a light source. That's just something that creates its own light, like the sun or a lamp or a candle. Everything else you see, from the screen you're looking at to the moon and the sky, that's an illuminated object. We only see it because light from a source is bouncing off of it. Now, to make all this stuff easier to understand, physicists came up with a great simplification. They imagined light traveling in these perfect straight lines called light rays. Now, is light really just a tiny little arrow zipping through space? Well, no, not exactly. It's way more complex. But this model, this idea of a straight ray, is so brilliant because it lets us predict and make sense of almost everything we experience visually. It's the foundation for our whole journey. All right, so what happens when these light rays actually hit something? Well, the very first thing they can do is bounce. And this super simple act of bouncing, which we call reflection, is literally the reason we can see the world and even ourselves. Yeah, reflection is really just a fancy word for light bouncing. The best way to picture it is to think about a tennis ball hitting a wall. If you throw it straight at the wall, it comes straight back to you. If you throw it at an angle, it bounces off at that very same angle. Light rays follow that exact same rule when they hit a smooth surface like a mirror. So, when you look into a regular flat mirror, light rays from your face travel to the mirror, bounce off, and then go into your eyes. Here's the trick, though. Your brain is hardwired to assume light always travels in a straight line. It has no idea a bounce just happened, so it traces those rays backward to a point that appears to be behind the mirror. This creates what we call a virtual image. It looks totally real, but it's not physically there. You can't touch it. But things get way more interesting when we start to curve the mirror. A concave mirror, just think, it curves inward like a cave, gathers all the light rays together into a single focal point. This is what a makeup mirror does to magnify your face. The opposite is a convex mirror. It bulges outward. Instead of gathering light, it scatters it, which gives you a much wider view. That's exactly why they're used for the side view mirrors on your car. So the big takeaway here is that the shape of the mirror changes everything. A plain, flat mirror gives you that perfect, same-size virtual image. A convex mirror, the one that bulges out, always gives you a smaller virtual image. And that versatile concave mirror, it can either magnify things up close or even create what's called a real image, which is an image you could actually project onto a screen. Okay, so light bounces. We got that. But what about our bent straw? That's not bouncing. That's the second major rule of light. It bends. This bending has a name. It's called refraction. And it happens because light travels at different speeds in different things. It goes faster through air than it does through water. So, as the light coming from the underwater part of the straw leaves the water and enters the air, it speeds up, and that change in speed makes it bend. Our brain, which doesn't know the light just took a turn, assumes it came in a straight line, and so it creates that image of a broken straw. And this is exactly what lenses are for. They are tools that are perfectly shaped to control this bending. A converging lens, which is thicker in the middle, bends light rays inward to a focus point, just like a concave mirror does. And a diverging lens, which is thinner in the middle, spreads the light rays out, just like a convex mirror. See the pattern? One reflects, one refracts, but the goal is the same. Now, this is where refraction gets even weirder. Imagine a light ray trying to escape from under the water back into the air. As you make the angle it hits the surface from below steeper and steeper, you eventually hit something called the critical angle. At this exact point, the light doesn't escape anymore. It just skims right along the surface. It's like a point of no return. So what do you think happens if we push past that point? If we fired the light ray at an angle that's even steeper than this critical angle, does it just get stuck? It gets trapped perfectly. Instead of bending out into the air, the light ray reflects off the inside of the surface as if it hit a perfect mirror. This is called total internal reflection. And even though it sounds really exotic, it is one of the single most important principles in all of modern technology. So how is this useful? Well, it's the technology that makes high-speed internet work. I'm talking about fiber optics. These shoot tiny pulses of light down a super thin glass fiber. The light hits the inside wall of the fiber at an angle way past the critical angle, so it reflects perfectly. It just keeps bouncing and zigzagging down the fiber for miles and miles without ever escaping, carrying all of our data with it. So we know light bounces, and we know light bends. Now, let's put it all together and see how we've built amazing instruments that let us see the world in completely new ways. A camera is just a perfect example. First, the diaphragm opens up to control how much light gets in. Then, the shutter opens for just a split second. And finally, a converging lens inside uses refraction to bend all those light rays into a sharp, focused image right on the camera sensor. It's all just applied optics in a little box. But for all of our incredible inventions, the single most sophisticated optical instrument we know of is the one you are using right now. The human eye. It has a lens, a pupil that acts like a diaphragm, and it focuses light on a sensor called the retina. It operates on the exact same principles as a camera. It's just a biological masterpiece. And when the eye's focus is just a little bit off, we can fix it using lenses. If you're nearsighted, your eye focuses light just a little bit in front of the retina, making faraway things blurry. So we put a diverging lens in front to spread the light out just enough so it lands perfectly. If you're farsighted, it's the opposite. The eye focuses light behind the retina, so we use a converging lens to pull that focus point forward. It's such an elegant fix using the exact principles we just talked about. Which brings us to a final, much bigger question. We've seen how light travels, how it bounces, and how it bends. We know an eye or a camera is just a machine for focusing that light onto a sensor. But all of that is just physics. The light stops at the retina. So if the eye is just the collector, what is the process in our brain that turns these simple rays of light into the rich, colorful, meaningful experience we call seeing? That's a question that takes us way beyond optics and deep into the mystery of consciousness itself.